Imagine stepping into a high-tech laboratory. The lights are off, the room is dead silent.
Yeah, no scientists in white coats anywhere, right?
Exactly.
Yeah.
There are no researchers huddled over whiteboards, no frantic typing. Yet, on the servers humming quietly in the corner, a massive data set regarding, like, a rare disease is being parsed.
Just churning through the numbers.
Right. A completely complex predictive model is being coded from scratch, tested, debugged, and finalized by a team of researchers who literally do not exist. Today, we are looking at a breakthrough that makes this kind of ghost ship laboratory a reality.
It is a really striking image. But it gets to the core of the discrepancy in how we view machine learning today versus how it actually operates in practice.
So totally. Because the end user experience of AI is just seamless. You type a prompt, you get an image or an essay, and boom, you're done.
Right. But behind the scenes, building those models is notoriously grueling. It's not glamorous at all. You have highly specialized engineers spending weeks just wrangling messy data pipelines.
And tracking down obscure syntax errors in Python at 2 in the morning.
Exactly. Or adjusting tiny mathematical dials called hyperparameters, just hoping the loss curve finally trends downward. And, a loss curve is basically just a mathematical graph showing how wrong the AI's predictions are.
Okay, let's unpack this, because our mission today is to explore a brand new state-of-the-art paper from researchers at UC San Diego that completely shatters that manual, tedious reality.
It really does. It's a fundamental shift.
This is a custom-tailored deep dive into a system called AIBuildAI. We have the technical paper, the architecture diagrams, all the performance benchmarks.
The whole package?
Yeah. And whether you are a seasoned developer who is absolutely sick of debugging neural networks, or you're just a curious listener wanting to know how the tech sausage is actually made as of May 2026, this is going to change how you view software development. AIBuildAI is an AI agent that automatically builds other AI models entirely from scratch.
Well, we should probably define from scratch carefully here, because, the industry has had automation tools for a while.
Right, like AutoML and stuff like that.
Exactly, AutoML. But AutoML is fundamentally limited. It generally just takes a pre-existing list of models and tweaks their hyperparameters. It's just turning dials.
So it still needs a human to set it up.
Yeah, it still requires a human engineer to fit the boundaries and define the search space. And then, more recently, we saw the rise of those basic coding agents.
Where you give a large language model a prompt saying, write me a model to predict house prices or whatever.
Right, and it tries to spit out the entire code base in one single output.
Oh.
But AIBuildAI bypasses both of those paradigms entirely.
How so?
It automates the complete lifecycle. You hand it a text description of your goal and a folder of raw data, and it hands you back a fully trained, highly optimized, deployable model.
Wow.
And it even gives you the inference script to actually run it.
That is wild. To understand why AIBuildAI is such a massive leap, I think we have to look at why those previous coding agents hit a brick wall.
Yeah, the single prompt approach.
Right, because on paper, just ask the AI to write the AI sounds perfectly logical. But I look at those single prompt coding agents like a short order cook trying to run a Michelin star restaurant entirely alone.
That is a great way to put it.
Right, like they're trying to chop the vegetables, cook the intricate sauces, plate the food, serve it, and wash the dishes all at the exact same time. They have to hold every single step in their head.
And that's exactly where they fail.
So if those traditional LLM coding agents fail because they simply forget instructions or get confused by juggling too much information, what we call context overload, how does AIBuildAI avoid that exact same trap?
What's fascinating here is the architectural shift. AIBuildAI completely abandons the single-agent approach.
So it doesn't just use one big brain.
No, it literally mimics the organizational structure of a real-world AI research lab. It relies on a hierarchical, multi-agent architecture.
Oh, wow.
Yeah. Instead of one massive prompt trying to juggle the dataset schema, the mathematical theory, the Python code, and the error logs all at once, AIBuildAI initializes multiple parallel workspaces. Think of them as isolated virtual laboratories.
And then it uses specialized sub-agents to operate within those specific spaces.
Exactly.
So it basically fires the solo short order cook and hires a specialized kitchen staff,
Yeah, exactly.
a prep chef, a saucier, a dishwasher. That makes a lot of sense. It completely sidesteps that whole context explosion problem. Because an LLM has a finite working memory, right?
Right, the context window.
Yeah, if you shove the entire history of a project into its context window, it starts hallucinating and making things up.
It just loses the plot. But here, the agent writing the code only cares about the code. It doesn't need to hold the grand mathematical strategy in its memory.
And the agent tuning the model only cares about the training metrics.
That isolation is the secret ingredient, really. Because these subagents have clean, focused context windows, they can execute multiple rounds of deep reasoning and tool use without overwhelming the underlying language model.
So they can just iterate in peace.
Exactly.
All right.
The coder subagent can write a script, execute it, read the inevitable error log, rewrite the code, and test it again. I mean, dozens of times, entirely within its own bubble.
I really want to look at this virtual staff in detail because reading the paper, the system architecture looks less like a software program and more like an organizational chart for a Silicon Valley startup.
It really does.
Walk me through the roster. Who do we have?
Well, at the very top, you have the manager agent. This is your technical lead.
Okay.
And the manager doesn't write a single line of Python. Its entire job is just strategic oversight. It reviews the execution history across up to 7 parallel solution paths and decides which subagent needs to step in next.
Oh, so it's just allocating resources and making the hard calls, like project path 3 is a dead end, kill it, let's focus on path 1.
Precisely that. It's just managing. Next, you have the setup agent. Think of this as your IT support.
Essential, but not glamorous. We all need good IT support.
Very true. It runs right at the beginning to prepare the Conda environment.
Oh, right. And for those not deep in Python development, a Conda environment is basically a fenced-in playground for your code.
That's a good analogy.
Yeah, it ensures that all the specific software libraries and package versions you need are installed without conflicting with anything else on the computer.
Right. So the setup agent builds that playground and then just gets out of the way.
Got it. Who's next?
Then we get to the core trio. First up is the designer subagent. This is the lead architect. It looks at the task, searches the internet for current best practices, and generates a comprehensive modeling strategy.
So it's actively Googling or web searching for how to solve the problem.
Yes, exactly. And crucially, it remains on standby. If a model is failing later during the coding or training phase, the manager brings the designer back in to analyze the failure and revise the blueprint.
That is so cool. And then following the blueprint is the coder subagent, right?
Right. This is the engineer in the trenches. It takes the designer's high-level mathematical plan and translates it into executable code.
And I imagine it doesn't just write blindly.
Oh no, it runs short little sanity check tests on small subsets of the data. It iteratively debugs until the script actually runs without crashing.
Because Python scripts always crash on the first try.
Every single time.
Yeah.
Once the code is stable, though, the tuner subagent takes over. The tuner is the optimizer. It runs the full training loop and monitors those loss curves we mentioned earlier.
So it's tweaking the hyperparameters methodically.
Exactly. For example, it might adjust the learning rate, which basically dictates how drastically the AI updates its beliefs after seeing a new piece of data.
Or like the batch size, which is how many data points it looks at before making an update.
Right. The tuner runs all these experiments to squeeze out the absolute best performance.
And finally, we have the closer, the aggregator agent.
The aggregator, yes.
When the strict time limit runs out, the aggregator evaluates all the different models that survive the whole process.
And it has two choices. It either picks the absolute best performer, or it creates a weighted ensemble.
Which means intelligently combining the strengths of multiple different models to create a final, super model.
Exactly.
But let me stop you there, because the paper mentions a strict time limit. Who or what is actually powering these virtual employees? What is the underlying brain behind all these agents?
So the intelligence driving every single one of these personas in the study is Claude Opus 4.6.
Okay, wow.
Yeah, but the researchers set rigid boundaries to test the system's efficiency. AIBuildAI is given a 24-hour time budget and access to a single NVIDIA A100 GPU per task.
Wait, just one GPU?
Just one.
That is a massive constraint in modern machine learning. I mean, that forces the manager agent to be incredibly strategic about what experiments it greenlights.
Exactly. It cannot brute force a solution by running 1,000 models simultaneously. It has to actually think, plan, and execute efficiently.
I am going to push back here, though.
Sure.
Because having a brilliant organizational chart of AI agents chatting with each other sounds great in theory. But anyone who has worked in corporate America knows that a team of specialists can sometimes just result in endless meetings and zero actual output.
Oh, absolutely.
So does this multi-agent setup actually translate to viable, real-world software?
It translates remarkably well, actually. The researchers tested this on MLE-Bench.
Right, the benchmark.
Yeah, it's a grueling benchmark consisting of 75 Kaggle-style AI development tasks. And Kaggle is a platform where the best human data scientists compete to solve incredibly difficult corporate and scientific problems.
Right, so how did it do?
As of the March 18, 2026 leaderboard, AIBuildAI ranks first.
First overall?
First overall. It achieved a 63.1% medal rate.
Wait, 63% on Kaggle tasks is objectively impressive, but let's be honest about benchmarks for a second.
Okay, fair enough.
Kaggle datasets are notoriously clean. They are pre-packaged, perfectly labeled, neatly organized, but real-world scientific or corporate data is just a complete unstructured mess.
That's very true.
Does this paper actually prove the system can handle complex multi-step problem solving, or is it just really good at taking standardized tests?
That is the exact right question to ask, and it is why the breakdown of that 63% is so important. If we connect this to the bigger picture, AIBuildAI specifically dominated the high-complexity split of tasks on MLE-Bench.
Oh, really?
Yeah, it scored 46.67% on the absolute hardest tier of problems.
The ones that aren't just simple classification.
Exactly. These are not simple, clean data sets where you just apply a standard algorithm. These tasks require multi-step data processing strategies, bespoke architectures, and extensive algorithmic tuning.
So it's not just fixing typos in a Python script.
Far from it. Baseline systems like ARA Dojo, they treat AI building merely as a search over code solutions. They look at a script and say, how can I optimize this loop?
Right, just tweaking the syntax.
But AIBuildAI's multi-agent reasoning allows it to recognize when a foundational strategy is totally wrong, scrap the architecture entirely, and design a completely new approach from the ground up.
I need to see this in practice to fully grasp it because the paper outlines a few specific case studies that are fascinating. Let's start with the visual task. Identifying contrails.
The satellite imagery one.
Right. So contrails are the condensation trails left behind by airplanes. Finding them in satellite imagery is what we call a semantic segmentation problem.
Right. You want the AI to look at an image and color in exactly which pixels are clouds, which are empty sky, and which are contrails.
Exactly. So how did the virtual lab handle this?
Well, the designer agent initiated the process by proposing 7 different modeling plans. It pulled from established visual architectures like UNet, DeepLab v3 plus Rig, and Convex.
And the manager reviewed these, right?
Yeah, the manager reviewed them and narrowed it down to 4 to actually build, given their compute limits.
And those architectures aren't random. Like, a UNet is famous in medical imaging for finding incredibly precise pixel boundaries.
Exactly.
While something like Convex is great for understanding the overall features of an image. So the AI is making educated architectural bets here.
Correct. The coder implemented them, and the tuner ran the initial training. But early on, the manager noticed the UNet plan was struggling. The error rates were just too high.
So what did it do?
It called the designer back in to revise the mathematical blueprint. The designer researched the specific failure mode and decided to swap out the standard loss function for a Laveau's dice loss component.
I want to pause on that because that is a brilliant pivot.
It really is.
If you are listening and you aren't familiar with segmentation math, a standard error metric might look at a picture of a massive sky with one tiny contrail and say, well, 99% of the pixels are empty sky, so I'll just guess sky for everything, and I'm 99% accurate.
The classic class imbalance problem.
Exactly. The AI thinks it's doing a great job, but it missed the one thing you actually care about. But the Laveau's dice loss function mathematically forces the AI to care about the intersection and shape of the rare object, rather than just overall pixel accuracy.
Right.
The fact that the designer agent identified that specific mathematical trap and pulled that specialized formula out of the literature to fix the code is just staggering to me.
It is a level of deductive reasoning we simply haven't seen in automated pipelines before. And the process didn't stop there.
What else did it do?
At the 24-hour mark, the aggregator evaluated the final models. It didn't just pick the UNet. It realized the UNet and the DeepLab v3 Plus models were making slightly different kinds of errors.
Oh, so it combined them.
Yes, it ensembled them. It combined their predictions to achieve a winning score that outperformed either model alone.
Here's where it gets really interesting, though. Satellite images are one thing, it's visual data. But the paper details how AI tackled a medical task, classifying harmful brain activity from raw EEG time series data.
Yeah, the EG task is wild.
We are talking about reading actual, messy human brainwaves to detect seizures or abnormalities.
And time series data is notoriously noisy, especially in medicine. So the designer agent proposed a dual-branch architecture for this.
Dual branch.
Yeah, it realized that looking at the raw numbers sequentially just wasn't enough. So one branch of the neural network was coded to process spectrograms.
Which are essentially visual representations of the frequencies over time, right?
Exactly. It turned sound-like waves into pictures.
But it didn't stop at the pictures.
No, it didn't.
The other branch of the architecture applied something called a double banana montage.
Which is a great name.
It sounds like a dessert, but it is a highly specific, very real neurological term.
Right.
It refers to a specific physical arrangement of electrodes on a patient's scalp, looking at the voltage differences between specific pairs to filter out background noise.
And think about what that means. The AI searched the medical literature, found this human clinical technique, wrote the Python code to simulate that spatial arrangement from the raw data, and then fed that refined signal through a 1D convolutional neural network.
It's unbelievable.
And the final piece of that puzzle was the fusion. The system took the visual spectrogram branch and the raw double banana branch and wired them together using an MLP head.
A multi-layer perceptron.
Exactly.
Yeah.
The MLP acts as a final judge. It takes the output from the visual side and the temporal side, weighs the evidence from both, and makes the final medical diagnosis.
It built a multimodal medical diagnostic tool autonomously.
Entirely autonomously.
There is one more example in the paper that highlights the aggregator agent's intelligence. It was a task called Alaska 2 image steganalysis.
Oh, way.
And steganalysis is the practice of finding secret, hidden messages buried inside digital image files.
Right, detecting subtle pixel manipulations. To solve this, the aggregator didn't just average the scores of a few models, it utilized test time augmentation.
What does that look like in practice?
It basically took the images and flipped them horizontally and vertically before feeding them to the AI during testing.
Which is a classic trick to force the AI to generalize. It stops the model from memorizing the specific orientation of a picture and forces it to look for the actual hidden patterns.
Exactly. It ran these augmented images through 4 completely different architectures, including EfficientNet and a customized ResNet 50.
And then how did it combine them?
Well, it used rank-based blending.
Okay, rank-based blending.
Yeah. Instead of trusting the raw probability scores, which can sometimes be overconfident, it looked at how each model ranked the images from most suspicious to least suspicious and intelligently blended those ranks.
Wow.
It is doing incredibly sophisticated ensemble engineering that usually requires a senior data scientist.
This all sounds phenomenal, truly, but let's bring this back down to earth for a minute.
Sure.
If AIBuildAI is this capable, why isn't it deployed across every Fortune 500 company right now? Because there is always a catch.
There is always a catch. And the bottleneck here is cost.
Cost.
More specifically, token consumption. The Claude Opus 4.6 meter is just running constantly. You have multiple sub-agents chattering back and forth, writing hundreds of lines of code, reading massive error logs, revising long mathematical plans, and it is all being processed by a massive state-of-the-art language model.
Right. The compute cost per task has to be astronomical.
It is. It's very expensive.
It's like hiring a Nobel laureate in physics to format an Excel spreadsheet for you.
That is exactly what it is like.
Using the immense reasoning power of Claude 4.6 just to install conda packages or figure out why a comma is missing on line 42 of a Python script is massive overkill.
Huge overkill.
So if token cost is the fatal flaw, I assume the only way around that is either shrinking the model or restricting when it's allowed to speak.
You've hit on the exact solution the UCSD researchers are pursuing. The paper outlines 3 future directions, and the first is dynamic LLM routing.
Dynamic routing, okay.
The idea is to delegate the routine, simple tasks, like fixing basic syntax errors or installing packages, to much smaller, cheaper open-source models.
Oh, that makes sense.
Yeah, you save the expensive heavy hitter, Claude 4.6, exclusively for complex architectural design and high-level strategy.
That immediately cuts the cost. What's the second direction?
Resource allocation. As we discussed earlier, AIBuildAI was artificially constrained to 1 GPU for benchmarking.
Right, the 1A100 limit.
But real-world corporate models require multi-GPU environments and distributed training. So the system is being upgraded to dynamically scale its experiments across massive compute clusters.
Meaning it will learn how to balance network bandwidth and memory constraints on the fly.
Exactly.
And the third limitation.
Well, right now, the designer agent relies on generalized web searches to find architectural blueprints.
Right. Googling for loss functions.
Yeah. The researchers envision building a structured knowledge base.
What would that look like?
It would be a highly organized, instantly retrievable internal database of AI modeling strategies. Basically, a curated library of what works, what fails, and why, categorized by data type.
So what does this all mean for you, the listener? Let's say you are a domain scientist. Maybe you are a biologist mapping out gene expression in cancer cells, or a material scientist looking for new battery compounds.
You've got data.
You likely have mountains of incredible hard-earned data, but you probably lack the specialized hardcore AI engineering skills to build a bespoke neural network to analyze it. AIBuildAI bridges that exact gap.
It really does.
It means the ability to transform your raw experimental data into a deployable, state-of-the-art AI model is about to become as accessible to you as opening a web browser. You won't need to secure funding to hire a 6-person machine learning team just to find the insights hidden in your data.
And that democratization of AI development is the immediate near-term impact. But I want to leave you with a final thought, building on that idea of the structured knowledge base. Right now, AIBuildAI is entirely derivative. It searches the internet for human-created architectures. It reads our research papers and implements our ideas, like the UNet or the double banana montage.
Right, it's just copying us really well.
Exactly.
Yeah.
But consider what happens when this system begins updating its own internal knowledge base after tens of thousands of automated runs.
Oh, wow. I see where you're going with this. It starts accumulating empirical experience across entirely different scientific fields.
Exactly. It's highly likely that within a few short years, a system like AIBuildAI won't just be implementing human strategies. It will begin cross-pollinating concepts.
Like mixing biology and physics algorithms.
Yes, it will combine temporal fusion techniques from astrophysics with spatial modeling from genomics to invent entirely new, alien mathematical architectures that human engineers would never have conceptualized.
That's incredible.
It won't just automate machine learning. It will change the very fabric of how machines learn.
We started by comparing AI development to a single mechanic hammering together a sports car in a dusty garage. What this paper proves is that AIBuildAI isn't just building a fully automated factory to replace that mechanic.
Not at all.
It is building a factory that might soon start designing engines that rely on physics we don't even understand yet.
Yeah.
And that is a fascinating and slightly terrifying place to leave it.